All right, I asked for it and they gave it. So here we have New Horizons in Simulating Quantum Matter by Andrew King and D-Wave.
Hey everybody, thank you very much for being here and for sticking around until the bitter end. I realize I'm now the only thing standing between you and the reception, so I'll try to keep it brief. Today I'm going to talk about new frontiers in quantum simulation, and I'm actually going to talk about some old results, some results that are going on right now, and then some future results. The last time I was at Qubits was about 9 months ago, and I was talking about our new preprint, which has just recently appeared in Science, having passed the peer review process, and it's called Beyond Classical Computation in Quantum Simulation. So I'm afraid I might disappoint a few of you because Murray made it sound like I was going to go through everything in gory detail. But I'm just going to give a high-level overview, and anybody who wants more details can come and talk to me later.
Well,
I'm
so
also going to talk about
disappointed.
some other results that have been enabled with the higher qubit quality and qubit connectivity of the Advantage 2 processor. So all the simulations I'm going to talk about are related to phase transitions. So we've heard a couple of times the example of water freezing into ice at a critical temperature, Tc.
Right.
And if we can see a certain crystal structure forming in that ice, that's because of the dynamics of the phase transition. So that's what we're going to be simulating.
Okay.
Now, we don't just need to have a changing temperature for a phase transition. We could also have different phase transitions, and we can have phase transitions at absolute zero. This is called a quantum phase transition, and it comes about when changing another parameter other than temperature. So one of the parameters, in fact, our favorite parameter to change is the transverse field. So you're tuning quantum fluctuations. And so you're guiding a disordered system through a quantum critical point towards a more ordered system, whether it's glassy or ferromagnetic or geometrically frustrated. And a classical and quantum phase transition can exist in the same material, in the same phase diagram. You just need a temperature axis and a quantum fluctuations axis. So temperature is thermal fluctuations. And this is basically the phase diagram of a three-dimensional spin glass optimization problem. So if you are a business customer and you want to optimize something, you don't necessarily care about how you get to the best answer. You just want to get there, and you want to get there fast. But it can make a big difference which phase transition you go through. So if you go through the thermal phase transition, you get different dynamics than you do when you go through the quantum phase transition. So I'm going to demonstrate I'm going to talk about the first experimental demonstration of this at large scale that we performed and published in Nature in 2023. Now, D-Wave started over 25 years ago, and we must have had some inkling that quantum annealing would be fast. So this actually comes from a few different threads of research that were all occurring around the same time about 25 or 30 years ago. So I'm just going to mention a couple of them. The first came from MagLab experiments. And in these experiments, researchers would take literally a chunk of a disordered alloy, which is effectively an icing type three-dimensional spin glass, and they would put it in the sample holder and they would subject it to a magnetic field that is transverse to the icing moment. So this is literally an experimental implementation of quantum annealing. And they found that this quantum annealing method, by attenuating quantum fluctuations, they could guide the system towards low energy states faster than they could by thermally annealing the system. So this is exactly what we're going to reproduce 25 years later in a programmable quantum material. And another piece of evidence came from Monte Carlo experiments a few years later by Santoro et al. In Science in 2002. And they studied some two-dimensional spin glasses and compared simulated thermal annealing and simulated quantum annealing. And they found, you can see these two slopes here. One is steeper than the other. And I'm going to get a little bit more into that later. But the quantum one is steeper. But it's not the real quantum one. It's a simulated quantum one. And this Monte Carlo simulation has the right equilibrium properties, but not the right dynamics. So I'm going to compare that to real quantum dynamics as well. So anyway, we have some evidence that quantum annealing should be fast. And so now we need to show that we can actually do quantum annealing as it's expected to be done. Now, in the beginning, at D-Wave, everything was rather slow. And as we've developed these processors, the coherence has gotten better and better with each generation. Mm-hmm. So in 2018, D-Wave published a paper in Science detailing the finite temperature phase diagram of three-dimensional spin glasses. So if any of you are computer scientists, you might think that the Platonic ideal of a hard problem is 3-sat, some sort of 3-sat problem. For a physicist, it might be a three-dimensional spin glass. These are NP-hard optimization problems. They correspond to real materials, as I just mentioned, and they are convenient to study. But we don't really want to study. You can see the annealing trajectory in this picture, and it's actually. I'm going to stop there. You can see that it's actually finite temperature. This is the temperature axis, and it's finite temperature. Why? Because we're not coherent through the computation. So we're coupled to the thermal environment, and it's cold, yes, around 12, 15 millikelvin, maybe a bit lower, maybe a bit higher. But it's there. And we don't want it to be there. So 5 years later, we managed to explore the zero temperature quantum phase transition of the same effective system. And by doing this, we can get at the real quantum dynamics, which are a lot easier to model than the open quantum dynamics. Okay. So one thing that people often say is that D-Wave, one of the things that you can do that classical methods absolutely cannot do is simulate open quantum systems. So quantum systems with a thermal environment. But we don't always want to do that. But sometimes we want to show that it is exactly the quantum system that we would expect. So that's what we're doing here. Mm-hmm. And what do? We go through this quantum phase transition, and we change the rate at which we pass through it, the velocity. So this velocity, well, it's an annealing time. So how long do you take to get from the beginning to the end? And as you lengthen that annealing time, you drive to lower and lower residual energy. If you are trying to solve an optimization problem to save money, the residual energy is how much money is left on the table when you've finished with your work. Now, we don't just have experimental evidence that quantum annealing is faster than both simulated quantum annealing and thermal annealing, simulated annealing. We have theoretical evidence, and these theory lines are shown here. And you can see that we're adhering very well to the theory line in quantum annealing. We're a little bit less steep, and then everything goes to hell around 100 nanoseconds. And this is because we're decohering and we're getting thermal effects. Now, this was on an Advantage 1 processor or an Advantage processor. If we repeated this same experiment on the Advantage 2 processor, we would see, as we did in Pau's talk in the scientific session today, we would see that the energies would be about twice as low, and the continuation along the theory line would be not only a better slope, but it would continue longer before it started to bounce from the thermal environment.
Okay.
So just as it was foretold by Santoro et al. In 2002, indeed, we saw that also in a three-dimensional spin glass, we saw that simulated annealing is slower than simulated quantum annealing, and we showed that quantum annealing is faster than both of them. So this is a quantum speed-up and approximate optimization, and we did this at a 5,000 qubit scale. So I'm going to step away from optimization now. That's kind of a mix of simulation and optimization. But this is like not only showing that we have a quantum speedup in an optimization problem, but also explaining why based on quantum critical phenomena. So it's kind of a very satisfying result that's tied up in a neat bow. But I'm going to get away from that. I'm going to talk about supremacy demonstrations. And I'm really going to talk about simulation of quantum dynamics. So we're not just trying to optimize a classical objective function anymore. We're going to try to predict or model what happens to a quantum system as you drive it quickly through a quantum phase transition. So if you drive it quickly through a quantum phase transition, you fall out of equilibrium. And as you fall out of equilibrium, the system kind of scatters into a probability distribution of excited states, ground states, lots of different energy levels. And it's very hard to predict and sample from this distribution unless you can really simulate the quantum dynamics. And it's generally accepted that, in general, simulating quantum dynamics is hard, especially at dozens or hundreds or thousands of qubits. So what we did in this paper, and now I'm talking about the science paper that came out a couple of weeks ago, we did more than is just on this slide. We actually did, now that I'm counting, we did 6 different lattices. So we did one-dimensional, just as a reference in the back matter. We did two-dimensional, and we did 3 different kinds of 3-dimensional lattices, and we did biclique lattices, which are infinite dimensional. Okay. So the reason that we studied these lattices is because depending on the dimensionality of the system, you get different critical behavior based on the quantum phase transition. So these should have different characteristics that don't depend on the local specifics of the lattice, but the general dimensionality of it. And we see that that is indeed the case.
Okay.
For simulation size, we used a Z6 processor, and we didn't try to use all of it. We just tried to scale up the lattices naturally. So we went from 16 qubits to 567 qubits in this experiment, and we can go much bigger in the Z12 that's recently been calibrated. Mm-hmm. We also explored a variety of evolution times. Now, evolution time, you can think about this as the depth of the simulation. So as you evolve slower and slower, not only do you drive down the residual energy, but you also lengthen the correlations. And as these quantum correlations spread, it becomes difficult to simulate. So there's actually 2 very easy limits in this problem. At the very fast annealing, it's easy because there are hardly any correlations, and they don't interact in a complicated way. If you anneal very, very slowly, then you can actually reduce the problem to a classical optimization problem, or a slight variant thereof. So we want to be between this. And actually, the long anneal limit is just a function of system size. So we want to do deep simulations. So we went up to 40 nanoseconds, and we calculated a bunch of different material properties. In figure 1 of the paper, we laid out the computational task. The computational task is to sample from the distribution of states following this dynamics. So, of course, we get full samples, and we also get 4-body correlations and 2-body correlations, which are very important for indirectly validating the largest simulations where you don't have a ground truth, because you can't simulate it classically. Now, people have been working on this since we put our preprint on the archive. And this is great because it really helps to refine the limit of what classical methods can do. And they pushed this limit forward further than we did. And the direction that they pushed this from was the fast anneal limit. So when things are very fast, they're easy. And they did this a little bit longer than we were able to. And this is great, but the only bad thing about it is how it's misinterpreted in the public discourse. So I feel like I should point out what they didn't do, which is simulate the biclique lattice because their methods don't apply. They demonstrated up to 54 qubits, although in principle they should be able to go larger. And they went up to 40 nanoseconds, and they only did one of the 2 types of spin glasses that we studied. And they only did 2-body correlations, so they didn't do higher cumulants or full samples. So there's no suggestion there from the authors, although other people have suggested it, that our results have been overturned. I just wanted to clear that up. So this is just to point out the scale of the simulations. This is the largest classical simulation that we got a ground truth for in the 3D case, and also that the Flatiron group simulated recently. And this is what we can do on the Z12 processor, which is 64 times bigger. It's a 12 by 12 by 12 lattice. And this is just a huge quantum simulation. And it's really not easy to do, even if you have what seems like an efficient classical algorithm. So let me get back to scaling. So assuming that you're not in this fast anneal limit and you have long correlation length, then what limits the simulability is entanglement. So you have to capture entanglement in the system. And the best way to do this is with a tensor train or matrix product state. So MPS is the method that we used. And if you're using MPS...
I kind of lost the plot. I don't know what you're simulating again.
Then your solution time will scale exponentially as a function of system size. So it becomes very hopeless very quickly. And we only went up to 500 or so qubits, and we can go much larger now. But even for biclique, cubic, diamond, all of these lattices, it becomes very hopeless to solve these problems with MPS, which is a bit inconvenient because we really want ground truths to validate our results, but we're then in a regime where we don't have these ground truths available. So we need to do an indirect validation. And the way that we do this indirect validation, I'm actually going to show you how to do it. We estimate the Kibble-Zurich exponent mu, and this is a bit technical. It's very technical, doing quantum Kibble-Zurich data collapse. But this is what we did, and what we're looking for to validate the results indirectly without comparing to a ground truth is that for each dimensionality, we get the right exponent. And sometimes there's a pencil and paper proof of what the exponent should be. For infinite dimensional and one-dimensional, that's the case. For 2- and 3-dimensional, the fact is that there are other methods to get at this Kibble-Zurich exponent mu, and so we need to check that our results are consistent with previous estimates. And they are. They are for all 6 of the lattices that we studied. Now, I'm just going to focus on one of them, which is the 2-dimensional case. And I'm going to focus on it because there was a paper published in Nature last year that studied this with a very heavy-duty classical Monte Carlo-based simulation. And they didn't only estimate the Kibble-Zurich exponent. They did a lot of other things, and it's a great piece of work. But one of the things that they did was provide this box for the 2-dimensional system. Mm-hmm. And so I'm going to show you how we can get at an estimate of this Kibble-Zurich exponent in 2 minutes using a D-Wave processor. So in the Z6 that we had last year, you can go up to 18 by 18. But in the Z12, you can go up to 32 by 32 with no defects. There's no missing qubits, no imperfections in this lattice. It's over 1,000 qubits. And this is considerably larger than what they did in the 2024 classical simulation paper. Mm-hmm. So I think the timing is not quite right, but this is basically how fast the results come in if you're running them on a D-Wave processor. It should take in total 2 minutes, and I don't think I'll talk about this for 2 minutes, even though I'm the last talker, so I can talk as long as I want. I think we're even a little bit ahead of time. But I will cut into Murray's time, and I'm not sure he's going to appreciate that. So anyway, a couple of jokes, and the results are in. So these results come in fastest for the 6x6 models, because I can pack lots of them into the Z12 processor. I can parallelize the computation. I also don't need very many of them because it's a small lattice, you don't need very good statistics. By the time you get up to 32 by 32, you need to put about 30 seconds of work into this. And I'm just assuming that these are coming in at a rate of about 10 per second, which is what I generally get with this type of simulation for full utilization of the processor. I might have to use 2 laptops to do that, but only 1 QPU. So how are we going to estimate mu? We're going to calculate the Binder cumulant, which is this U on the y-axis. So this is based on 2- and 4-body correlations, and it's straightforward to compute if you have full samples. We're actually going to collapse this data in what is called a dynamic finite-size scaling ansatz. So you can see on the x-axis we have annealing time times the linear size of the lattice to the power of minus mu. And that means on this log-log plot, we're actually going to slide the data over as a function of the system size until it all collapses on a common curve. And as we do that, we stop when we get to the common collapse, and this is our estimate of mu. And it's fully consistent with the previous estimates and with the estimates that we got in 2024 as well. So this is a very fast way to get at an estimate of the Kibble-Zurich exponent. I'm just going to talk about three other quick examples of quantum simulation. This is one that we're just wrapping up, and basically because of all the stuff with the science paper, I haven't been able to finish this paper, so I apologize to Alejandro. If you were in his talk at the fireside chat, actually, he didn't talk about this one in the fireside chat, so I'll talk about it. We have a potentially cross-platform benchmark for quantum simulation, and this is on Ising fullerenes. It's kind of a fun problem, and the nice thing is that it gives a really good benchmark, and it can potentially be run on neutral atom systems as well, so we could get an apples-to-apples comparison. So they've actually shown about 7 years ago, I think, there was a paper that showed a buckyball in a neutral atom trap. So they can do it at least in principle, and I'd like to see them do it in a production system one day. So this is joint work with Alejandro Lopez Bezzania at Los Alamos National Lab. And what we do is we drive towards what's called a perturbative ground state. So basically, in theory, the slower you anneal, the closer you get to the optimal solution. But these are experimental platforms. Even the best of them decohere, and they have other sources of error. So what we want to do is we want to drive as slowly as we can, and we want to see what kind of simulation error we can get to. So this is an advantage to running the same problem, and these black X's are what the ideal quantum dynamics shows. So the black X's go to 0 error in the limit, and if you thermalize, so if you have decoherence, you eventually end up at thermal equilibrium. So you can see that advantage and advantage 2 end up at the same point on the far right, and that's the slowest anneal where you thermalize. But in the middle, you can see a qualitative difference between these two processors. And this has nothing to do with the connectivity, because we're doing the exact same problem. It has nothing to do with the size of the processor. It's all to do with the quality of the qubits, coming from the energy scale, the design of the qubits, and improved materials.
Right.
Another thing that I want to mention, this is future simulation. Maybe I'm going to do it, maybe somebody else is going to do it, but I would like to see it done on Advantage 2. So again, with Alejandro and Cristiano Nasoli at Los Alamos National Lab, we had a paper in Science in 2021 called Qubit Spin Ice. And this was a really fun project. We basically set up a wrestling ring, and we trap emergent magnetic monopoles in this lattice, and we see how they bounce off of each other or annihilate one another. But this was a challenge. We had to use every last bit of the D-Wave 2000Q processor to do this. So we also had to use 4 qubits per physical site, or per lattice site. In Advantage 2, we can do this with no embedding overhead, so it's a 1-for-1 simulation. We can also do it without holes. So you can see these horrible holes in our lattice. And these are really, they interfere with doing things cleanly. And we can also do larger lattices. So all in all, this is going to be a huge improvement on this experiment. And I would love to see this done on Advantage 2 to see if we can see some really interesting quantum effects in this qubit spin ice. Finally, I'm just going to mention quickly another work with Pratik Sathe at Los Alamos National Lab. And they're doing a simulation of the Villain-Onsager model. Now, this is a model where we're simulating a variable temperature, but we're doing it in a quantum annealer. So we're doing a classical simulation with a quantum annealer now. So we're simulating a temperature by tuning the strength of the classical terms, and then annealing very slowly. And this is actually, it's a classical simulation, but it's very hard to do. And the reason it's very hard to do, well, it's a bit technical. I'm not going to get into it. But one way to make this better and to make it work is you can actually embed a torus. So embedding a torus really gets rid of a lot of problems that you have with this simulation. And we're able to do this for the first time in a quantum annealer in Advantage 2. So good results require a torus, and this is a solved model with tunable frustration. I'm not going to explain what tunable frustration is, but a solved model means we know what the right answers are. We know it's a pencil and paper thing, and we know that the critical exponent gamma should be 1.75. And when we do this simulation, we measure the magnetic susceptibility on the left, and then we plot the height of the curve. Each color here is a different system size, and we plot the height of the curve on the right, and from the slope of this line, we derive the critical exponent, which we estimate to be 1.77. So that's very close to the answer, and so that's a nice result, which is enabled by the new connectivity of the Advantage 2 processor. So just to finish up, I've gone over some new frontiers in quantum simulation. We have a breakthrough result for quantum annealing. It's really helpful to be able to say, quantum annealing can do things that no classical computer can.
I mean, I guess he presented results. I mean, it's very much just here's something to make you a little more familiar. Go and read the paper. Yeah, I was hoping for something a little bit more down and dirty, and I was hoping for more physical intuition. Um, like when you talk about spin ice or like lattices, what should I imagine you're talking about? Um, when you're talking about simulating the buckyball, like I'm not sure I even understand what that means. You're simulating a buckyball. Like I just there's a lot of physical intuition that's just missing. Like what are you simulating? I don't really understand. Yeah, so it's just sort of like I guess an advertisement for the publication, but I mean it's just like I'm gonna need to go through the paper, and it doesn't look appealing because it looks like the paper is probably barely, like I have a fear now that the paper is not going to be well written enough. It's not going to talk about physical intuition. It's not going to be a nice story walking me through. It might just be a lot of what appears to be gobbledygook, and I'm gonna have to figure out the rest myself. Um, yeah, I don't know. I'm a bit disappointed with this one. I mean, I guess it's a little bit of a sample set, but I mean, you get like a little bit of a sample platter, but not really. I I'm not sure how this helps me.